Morning, students. Yesterday I was discussing about a bandpass system for which how a complex representation can be complex envelope, complex representation can be for the bandpass signals as well as individually bandpass systems we have considered. Now, when we are combining both the bandpass systems and the bandpass signals, mean to say that whenever a bandpass signal you are trying to pass over a bandpass system, what will be the net resultant effect of the bandpass signal over a bandpass system? That is what we yesterday I started discussing, and I'll be continuing in this class the same topic. And if you go for this bandpass system, we know that it is a system whose bandwidth is limited between minus b to plus b with center frequency fc, or with center frequency fc, or you can say that the whole bandpass system's bandwidth will be greater than or equal to 2b. And if to such a system, when the bandpass signal it is passed, and there are two types of signals we have considered, a narrow band signal and a bandpass wideband signal. Narrow band signal we are considering here, whose bandwidth is limited between minus w to plus w, centered at center frequency fc. Such a band limited signal whose bandwidth is lesser than or equal to, when it is passed through a bandpass system, how do the system can be applied, and the system will respond, and how these signals behaves over the bandpass systems I was discussing. Whenever a bandpass system you consider its impulse response, we know that it is its impulse response h of t, and to such a system, a bandpass signal s of t, we are what we are applying, and the output will be termed as x of t. There are two analyses we can make. One is the time domain analysis, and the other one is the frequency domain analysis. In time domain analysis, S of t as a bandpass signal passed through an bandpass system having an impulse response of h of t gives an output x of t, and this x of t and s of t, when you are considering, or your impulse response of a bandpass system you are considering, practically the bandpass system will have a deviation from its center frequency plus or minus delta f, and now the output for such small deviated time domain or frequency domain signals, when you are considering the response, how you are going to analyze. The very first beginning step of analysis of such bandpass systems and signals, when you are considering, the first step is to combine the effect of the bandpass systems with the bandpass signals. So how do you combine the bandpass signals with bandpass system? So for that we have considered, let the x of t be the output of an bandpass system with an input as a bandpass signal s of t. So whenever you have s of t pass through pass through an bandpass system having an impulse response, the output by definition you can get as, 1 minute, x of t, that is the output, it is equal to, in time domain, s of t, that is the bandpass signal, convolute with the impulse response of a bandpass system h of t. So this convolution process, when we are converting into an product, into product terms, so this x of t, the output of an bandpass system, you can re-represent as integral from minus infinity to plus infinity. This, since there is a deviation in time, so time with a deviation we are taking as delta t, that we are representing as tau. At tau, new time period, h of tau, multiply this with s of t minus tau into d tau. because they have been deviated. So you can call this as equation 1. And now this equation 1, if we are representing in the form of pre-envelope, how do you represent the pre-envelope of this? It is x plus of t is the pre-envelope of x of t, that is a bandpass system. It is equal to integral from minus infinity to plus infinity. How do this h of tau you can replace? It is the real part of h plus of tau. Multiply this with real terms, a real part of s plus of t minus tau into d tau. So this is equal to half, because h of, by the property of h plus of tau, that is the pre-envelope, we know that 2h tau is equal to. So therefore, we have taken this half when we are considering only the real part from this pre-envelope. So now in terms of, okay, now this is what the pre-envelope of your x plus of t, that is the bandpass system. Now moving on to the next step. So let us using, this is what property we have used. Here we have, to get this one, we have used using the property of pre-envelope. Just pre-envelopes property we have used, and we have represented the whole bandpass system with a bandpass signal. Now, by definition, this is the pre-envelope. Okay, I think there is a mistake here. Okay, in terms of the pre-envelope equations, if you are representing in terms of pre-envelope, if you are replacing this h plus of tau and the s plus of t minus tau, how do you represent that? Anyhow, I'll write it in separate in the next page as a separate equation. So this x plus of t, that is the pre-envelope of an bandpass system, it is equal to half of real part of this. Half how you got, I told you it, that we are taken from the property of pre-envelope. So when we substitute pre-envelope, you will get half term. Minus infinity to plus infinity, h of tau, that h plus of tau I am replacing with h of tau into e to the power of j 2 pi f ct in, and which is one more term we are convolving. It is multiply this with, okay, I'll write it from here. Multiply this with s tilde, that is an complex envelope. In terms of complex and pre-envelope, we are representing pre-envelope equation. So s tilde of t minus tau into e to the power of j 2 pi fc into t minus tau into d tau. If you have any doubt until this part, you can ask me. Shall I continue? Students?
Yes, ma'am.
Yeah, I'm audible, right?
Yes, ma'am.
Yeah. Now, if you are going for, this is only we are taking for an x of t bandpass signal, it is not the pre-envelope. We have represented that x of t convolution values h of tau and s of t minus tau or s of t in terms of pre-envelope terms we have represented. So now further moving on to this x of t, it is equal to half of real part of. So you can replace this in this particular equation, which is the common term. you can take as e to the power of j 2 pi fct. Multiply this with integral from minus infinity to plus infinity. What are the terms you have? What are the terms? H tilde of tau. Just you please solve along with me so that it will be easy for your examination point of view, the learning into d tau. Into d tau. This is the whole thing. Any doubt till this point? Let x tilde of t, that is the complex envelope. So, okay, this here x tilde of t is the complex envelope that you can replace with half of integral from minus infinity. Here, in this equation, I am going to substitute x tilde of t as half of or s tilde, sorry, s tilde signals function, half of h tilde of tau into s tilde of t minus tau into d tau. You can call this as equation A. Substituting equation A in equation 2. So what is your x of t? Substitute A in equation 2. What you will be getting? X of t, which is equal to half of, please tell me, half I have taken here. What will be the left out terms? Students, be interactive. In the equation 2, I am substituting half integral from minus infinity to this whole term as s tilde of t as a complex envelope of the signal, baseband bandpass signal. So what will be this expression?
Real of s tilde of t per j 2 pi fc.
Part of, yeah, speak out.
S tilde of t e per j 2 pi fct.
Yeah, s tilde of t into e to the power of j 2 pi fct. This you can call it as equation B. Fine. Okay. Now we know what is the signal, baseband signal, when is a passband signal or bandpass signal. When it is passed through an bandpass system, how the output it is half an bandpass system is. Now, and in terms of pre-envelope, we have represented. So now the complex envelope we'll see. Complex envelope of x tau of t. Complex envelope of x of t is what? X tau of x tilde of t of output signal of what system? Bandpass system. Bandpass system. How do you get this output complex envelope of one bandpass system? Is a linear convolution of the complex envelopes of complex envelope of input signal. Complex envelope of input signal. Which is your input signal? Complex envelope of input signal and complex envelope of the impulse response. So how do you represent by equation? So what is complex envelope? You can consider, see now what we have considered. We have considered a system whose input is a complex envelope of an bandpass signal that we are passing through an linear filter having an impulse response of complex envelope H. So what you are getting is x tilde of t. So now we have to find out the complex envelope's response of this complete bandpass system. So it is equal to the whole definition I will be writing in terms of equation. So x tilde of t, it is equal to s tilde of t convolution with h tilde of t. Pre-envelope we are taking separately and complex envelope we are taking separately. Fine. So what is from equation A? From equation A. What is equation A? Please look at here. What is your equation A? S tilde of t is equal to half of integral from minus in h tau into h complex, that is complex envelope of h of tau with s. So what you can write, rewrite this equation, above equation as x tilde of t, which is equal to, from equation A, how do you replace this one? Half of integral from minus infinity to plus infinity h tilde of t, sorry, tau, multiply this with s tilde of t minus tau into d tau. Is it clear, students?
Yes, ma'am.
Just I have replaced this x tilde, substituted for x tilde of t from the previous equation. Okay, now half that I'll take it as towards the left. So therefore, you can see that here 2 into x tilde of t, which is equal to integral from minus infinity to plus infinity h tilde of t, multiply this with s tilde of t minus tau into d tau. This thing you can represent in terms of convolution as what? It is nothing but the convolution of the complex envelope of the bandpass signal convolved with the complex envelope of the impulse response h of t. So you can call this as equation C. Now let us consider the complex envelope x tilde of t. Now x tilde of t, when expressed in terms of in phase and quadrature component. In phase and quadrature component. How do you represent this one? How will be representing means x tilde of t, which is equal to s I of t in terms of the bandpass signals in phase and the quadrature component SQ of G. Okay, scale this whole equation by 2. Above equation, scale it by 2. Scale by 2 because we know 2x tau x tilde of t. So when I scale it by 2, left side will be 2 multiplied with x tilde of t, that is equal to twice the in phase component of a bandpass signal plus imaginary content of twice the quadrature component of a bandpass signal. You can call this as equation D. Now, from
It should be 2 into SI of t, no ma'am.
yes, ma.
2 into SI of t.
Yeah, sorry. SI of T. Now, from equation C, what is your 2x tilde of T? That is equal to, what is this portion that is equal to S tilde of T
Tilde of
equal with
into H.
yeah,
H tilde of t.
tilde of T. The complex envelopes we are. But now, when you replace this S tilde of T, convolution with H of H complex, that is when you represent this S tilde of T in terms of in phase component and the quadrature component. How do you represent this one? This is equal to quadrature component for this SI of T, right? Plus J into SQ of T. Convolve this with HI of T okay, I'll go for next page. So now 2 into x tilde of T, it is equal to S complex envelope of base bandpass signal convolved with complex envelope of impulse response of a linear time invariant system. I'll be re-representing this in terms of the in phase and the quadrature component. So how can you represent this as equal to SI of T plus J into SQ of T convolved with okay HI of T plus J into HQ of T in time domain convolution will be equal to the product. So therefore, how can I replace this expression HISI of T, multiply this with or convolve this with, correct? SI of HI of T plus, please tell me the words, terms, J into SQ of T convolved with HI of T plus J into, you just we are multiplying HQ of T convolved with SI of T minus J into J. So what you are going to get, that is equal to HQ convolved with sorry, HQ of T convolved with SQ of T, right? This term is okay. So therefore,
Yes, ma'am. Yes, ma'am.
X tilde of T, which is equal to two terms, you will get J term and imaginary and real terms. If I remove, separate it, HI of T convolved with SI of T minus, yeah, SQ of T convolved with HQ of T. Is it correct? Plus,
Yes, ma'am.
yeah, plus J into J terms. Yes, I convolved with HQ of T. So your T I missed. Plus, yeah, SQ of T convolved with HI of
HI of T.
yeah. So this is, you can call it as equation E. Compare now equations D and equation C. 1 minute. By comparing equations C with compare equations 2 and E. Compare equations C and E. Compare equations D and E. This is equation E. Equation D is 2x tilde of T. So what is 2 SI of T? Imaginary, in phase component. Imaginary component. We need to separate it. Okay. Comparing equation D and E. D and E. What we'll be getting means 2 SI of 2x of, just we are taking the in phase and the quadrature components. So it is equal to HI of T convolved with SI of T minus HQ of T convolved with SQ of T. This is one term. And then next term, the quadrature component of a bandpass system, that is 2xq of T, which is equal to SQ of T convolved with HI of T plus J into, J term I am taking out because imaginary and real factors real terms I am comparing. HQ of T in convolved with SI of T. So you can call this as equation 7. Now, what is the relationship between your in phase and the quadrature components? For a bandpass system, we'll representing equation 7 diagrammatically. Gives relationship between in phase and quadrature phase. Components response. A response of which system? Response of bandpass system. So now let us see that particular system, how we can represent. One minute. Okay, now what is the input that we are going to get? It is SI of t. Convolve this SI of t, pass it through one HI of t, that is giving you the convolution of SI of t with HI of t, that you need to add with SQ of t. After, when you pass it through an HQ of t, sorry, HI of t, it gives another term, and the same SI of t, when you are passing through another filter having its response as HQ of t, what is you are going to get? That you, when you sum it up, true and summer, you will be getting as 2 SI of t or 2 XI of t. The quadrature component, you will take this and pass it through an quadrature impulse response HQ of t. So when you pass it, you will get positive term. Sum it with summer with a negative term, what you will be getting is 2 XQ of t. Okay, this particular diagram, which gives a frequency representation, time domain representation of your bandpass signals and bandpass systems together. Fine. So this is about your various bandpass systems, signals, its time domain response, frequency domain response, and so on. Now, let us move on to the next topic. Line codes are signaling formats. What are line codes or signaling formats? This is the 6th topic in your syllabus, and this is your, there are 7 topics and last but 1 topic. If you are on this particular topic, they are asking you to draw the power spectral density or derive the expressions for the power spectral densities for various line codes, and otherwise they'll ask you to solve the problems. And on the 8th question, they'll be 8th topic, they'll be asking only the problems, okay, or they'll ask you to explain the format for and various schemes. Any of that I'll be explaining. Now, if you go for this line codes, first we should understand what exactly the line code are, the signaling formats. Why we are going for this line codes are signaling formats. Let us talk about this through the introduction. So any digital system, when you are considering, this digital system will take the input in the form of what? What is the data information that any digital system will take? Students, you have to respond. Yes, how the data will be taking. Speak out. How the digital system will be taking the information. How do, otherwise in simple terms I'll ask, how do the digital system will understand the information? Students, I need the answer from you. Otherwise, I'll go for PPTs. Instead of writing and explaining like this, I'll go straight away for the PPTs. What is the digital system? Are you there?
Yes, ma'am.
Yeah, what do you mean by digital system? What is the exact difference between a digital system and an analog system refers to? Please.
Ma'am, that represents the information by digits, ma'am.
Whenever any system, it is taking the information in the form of binary bits. Binary bits. Binary bits, then such systems are referred to the digital systems. These binary bits, how so far we have considered 0, it is the combination of, or it is 0 and 1, or combinations of zeros and ones, or it is the bit stream, continuous bit stream of zeros and ones. So sometimes the information will be considered only individual bit, through individual bit. Either it may be 0 or 1. Whenever entire information, it is getting transmitted digitally through 2 bits of signaling levels. So 0 or 1, it is termed to be a digital information. Sometimes instead of transmitting 0 and 1 individually, what we'll be doing will be grouping zeros and ones combination. For example, if you are considering 0 0 1 1 is an one example, 1 1 0 1 is an another example. How many bits we are grouping? 4 bits. So totally how many combinations of, when I take 4 bits to group digital information, how many combinations I can get? 16 combinations. Say for example, if I take 2 bits together to group 0 0 0 1 1 0 1 1. So totally how many combinations I am getting? How many combinations, students?
4.
4 combinations. Means my binary information I may transmit in the form of zeros and ones, or sometimes I may transmit in the form of grouping bits. If I group 2 bits, total number of combinations I can transmit as 0001, 10 or 11. If I go for more than 2 bits, like for example 4 bits, I'll get 16 combinations. So whenever I'm grouping more than 1 bit or a single bit, each time I'll be terming in digital as symbol. So whenever I'm referring to symbol, symbol is nothing but a group of bits which are used as an information for the transmission or for an digital system to make it understandable. So such informations are termed to be the digital informations. So systems which take such information are termed to be the digital systems. Now, if the system is taking the digital information, it will be in the form of symbols. But now the question arises, these informations, digital informations, we need to transmit over a transmission channel. It may be a baseband transmission or it may be a passband transmission. It may be a passband channel or a baseband or bandpass channel. When it has to be transmitted, my question is, can we transmit the 0 or 1 or the symbols directly over the channel? Can we transmit? Bhumika?
Yes, ma'am.
Other students are not there.
They are there, ma'am.
Yeah, Harshita?
Yes, ma'am.
Yeah, can we transmit these zeros and ones directly over the channel? Say yes or no. Whether it is wrong or correct, I don't mind. Because the correct answer, any of if you go wrong, I'll give.
No, ma'am.
Yeah, this 0 and 1 cannot be transmitted over a channel. The reason, they are not in the form of electrical pulses. Am I correct?
Yes, ma'am.
Electrical pulses. So now the question, in order to support for the transmission, because most of the information we will be transmitting through the channels, for the channels transmission, the digital data to be made compatible with the transmission channels. So thereby the concept of converting digital data to digital pulses will arise. Digital data to digital pulses. Digital pulses. Digital pulse. So what is the difference? How do you distinguish this digital data and digital pulse? Means you can look at here. There are different ways to represent this digital data. I take 0. I take 1. This is my digital data. When it is to be converted into an digital pulse, having a time duration of some bit duration, let me represent as TB. So 0 I'll be representing with a 0 volts for some duration, and this 1 I'll be representing with the same time duration having an amplitude of some amplitude. Let me call that amplitude as A. So now the conversion of digital data to digital pulse, why it is required? Because it is very much essential for the transmission over the channels, because there it is expected to be the information in the form of electrical pulses. So therefore we are converting the incoming bit stream 0 and 1 into the electrical pulses. Suppose I have 0, 1, 1, 0. How can I represent? Having a bit duration of TB for each bit if you take, and when you are converting this information into the electrical pulse form, so this is how you are going to convert. Okay, so this will be 0th bit. This is 0th bit, and this is 1, 1, and this is 0. So what is 0, 1, 1, 0, which is continuous with respect to time. So conversion of an discrete digital data into an discrete electrical signal is nothing but the signaling format. Understood what is signaling format? Why we are going for it? And how do this signaling format we will be getting from the discrete data into an electrical pulses? This is what we have to discuss in detail. So whenever these various signaling formats you are considering in digital communication, there are many digital formats or signaling formats you have. These signaling formats also termed as the line codes. Formats are line codes. For the transmission, digital data is made compatible to convert into an electrical pulse, and is termed to be the signaling formats or line codes formats. There are many different ways. These signaling formats can be derived from digital data. Different ways are different types. You have to derive these signaling formats from discrete data. The signaling formats, there are different signaling formats includes unipolar format. I'll explain what is this unipolar format or bipolar format or whatever it is. Unipolar format. The second one, it is the polar format. Polar format. 4 different types are there. Again, in each one, subdivisions are there. The third one is bipolar format. And the last one, it is the Manchester form. Manchester format. What do you mean by this? Each one is, let us take the first one, unipolar format. In this, there are the symbols what we are going to consider is 0 and 1. 0 and 1 only. The input for this unipolar signaling format is 0 and 1. 0 will be considered, 0 will be transmitted over a bit duration TB lesser than T greater than 0, having an amplitude of 0 volts. The one, symbol 1 is transmitted within this time interval, that is 0 to TB seconds with amplitude A. So how do you represent this one? A 0 with 0 of having TB duration, 1 with having an amplitude of A. This is suppose 0th symbol and 1 symbol, or 0th bit and 1 bit. I have, this is the bit duration TB, and again 1 also will be the symbol having its duration of TB. So in an unipolar signaling format, when it is converted into an electrical pulse, for an bit duration of TB, the amplitude considered will be 0 volts, and for bit 1, the amplitude will be considered as A. Is it clear, unipolar?
Yes, ma'am.
Yeah. Here in this unipolar format, 2 types are there. What are those two means? Non-return to 0, non-return to 0, and return to 0. I'll represent RZ and NRZ. So how this non-return to 0 and return to 0 for a particular signal we are going to represent will be non-return to 0 means unipolar non-return to 0. So please take the symbol as 0 and 1. So this particular thing will be representing like this. Okay. So here this is for the complete duration. There won't be any change in the amplitude. That is what non-return to 0. The return to 0 format. Return to 0 format is what means you have same, you take 0 will be as it is 0 from 0 amplitude from 0 to TB seconds. But when the symbol 1 it is considered, here the symbol 1 will have an amplitude of A for half of the duration or slightly more than duration, and rest it will go as okay 0. So this is for symbol 1 between time duration TB seconds. Non-return to 0, return to 0. It is TB by 2. TB by 2 or more than TB by 2, the amplitude will be high for symbol 1. Afterwards it returns to 0. This is non-return, return to 0 and non-return to 0 if it is of unipolar. Okay, this is the one signaling format in communication we will be using. So when this return to 0 and a unipolar format is used, easy to generate. Easy to generate means the complexity involved in generating the pulses for the bit combination zeros and ones, it is very easy. Simple circuits we can make use to generate this one. But disadvantage is that the DC component will soon get added. DC component adds to this DC component will add with this. Will get added very soon. The best example you can see that if there is a biasing condition and not properly stabilized, the amplifiers will have a DC component. So another best example you have in your third semester, clippers and clampers you have studied. The clampers, if you are taking an sinusoidal signal, if suppose there is an DC component when it gets added, how do this clamp will go? It will go above like this, right? 1 month. This it will be going. So negative portion will get clamped to the positive side. So this whatever from negative to 0, it is DC component induction. Such problems will be more in case of unipolar non-return to 0. But for a smaller distance communication, this type of signaling format can be used. I think I can stop.